Jenny. Thank you for organizing this. Do you see my screen?
Mhm.
Okay, play. And thank you, Lucy and Ali, for providing a lot of introduction that frees me up from, so I can present more during my talk. I just want to mention that this this work was done in collaboration with Jack Werner and Brendan Armstrong. In fact, the data were collected at UC Davis. So just to get them in there. We started off being interested in the question that Ali talked about, which arose from a hypothesis of Don McLeod that despite the reduced separation of the long wave cone pigments in the deuteranomalous and protoanomalous, leading to a kind of reduced input signal, there'd be some kind of neural compensation. And we were very stimulated by Ali's paper, and we thought that it might be interesting to try and measure this in a direct way with a novel scaling technique that's been introduced in the last 20 years. And our analysis, and this is using DeMarco, Pokorny Smith fundamentals sort of as an average anomalous observer, with the idea, with full knowledge that there's great individual differences because of photopigment ops and base substitutions, etc. But looking at the expected signal, chromatic signal on the LM cardinal direction, you could see by this reduction in the difference of the L and M, or the M prime M and the L and L prime cones. And if we just look at the peak to peak to trough separation with respect to normal, we'd expect to be on average kind of a 41% reduction for the protan and 25% for the deutan. So this is the reduced input signal. And the question was of whether we could, with a scaling approach, whether we could estimate whether there was some kind of compensation for that reduction at the input, so that the reduced input signal would be mapped onto the full neural response, as proposed by Don McLeod in his Reese lecture in 1981. Just to give you an idea of what the effect of the photopigment separation might be, if we assume that the contrast response for chromatic or for luminance contrast follows a kind of Michaelis-Menten function, we could think of the reduction in, so you have the contrast being dependent on there's a maximum parameter giving the maximum response RM, and another one, the semi-saturation constant, how fast this function rises. And then we have a kind of an offset, which has to do with the minimum contrast that the person can perceive reliably. But you can imagine that the pigment separation, the reduced pigment separation, is going to reduce by some factor alpha the input contrast. One way to, we could divide through by that factor alpha, and we see that just a completely equivalent expression. What that's going to do is that's going to move over the this minimum contrast, but it's also going to reduce increase the semi-saturation constant. Now, the maximum response is sometimes called the response gain, and this inverse of this semi-saturation constant is some kind of response gain. If we look at those curves on a log contrast axis, we see that this pigment separation is simply a scaling without any change of the shape. So if we want to really see a gain change, we really would expect that it would be some kind of change on this axis. We look there on this log axis where it's some increase in the slope that's different from that's over and above the scaling due to the reduction in pigment separation. Now, to get at this, we used a technique called maximum likely difference scaling that Ali referred to. The idea is that you take a set of physical values along a scale here, contrast, you see Gabor functions differing in contrast. And a prerequisite is that you can order them. They're all easily visible, differentiable, discriminable. And on any particular trial, we choose a triple, a triad, say A, B, and C. We present them like this with the fixation, and the task of the observer is to say whether the interval between A and B is whether is more similar, whether it's smaller than the interval between B and C. In other words, is the one on top, is it more similar to the one on the left or the right? Of course, we reverse randomly which one they're ordered, but the one on the left or right is randomly changed between trials. So it's a very simple task. Is the upper stimulus more similar to the one on the left or the right? The idea is that if you choose a stimulus where the choice is made about 50% of the time on both sides, then we can say that the perceptual interval between the two is equal. Of course, we can use the other judgments trials as well where they're not equal, and we can define a decision rule where we assume there are psychological responses, contrast perceived responses, for each of the stimuli, A, B, and C, and the observer is comparing the differences. And this difference of differences, when it's greater than 0, when you choose the one on the left, and otherwise you choose the one on the right, except that we assume that there's some judgment noise that's normally distributed, which has the effect of, with some unknown variance, sigma squared, which has the effect of when the intervals are quite similar, the observer doesn't always make the same judgment. Now, this task was introduced by Maloney and Yang, and there have been, in 2003, there have been a number of descriptions of it. And I just want to point to a review that came out this year, which summarizes the growing literature using this particular procedure. When we use this procedure for contrast, as you've seen here, here are two well-skilled psychophysical observers. This is, we of course, during a session, we present all triples, and this is the type of data from a skilled psychophysical observer that you can expect. You can see that it fits well this kind of Michaelis-Menten type psychometric function. So that's why I showed you that earlier. Now, one other thing, as I said, we were interested in this gain on the log scale, and this was actually a suggestion of Don McLeod to us when we were first writing this up. Instead of looking at the difference, the semi-saturation and the difference on the linear scale, we look at the ratio of the, for this value, the ratio, which would be the log of the differences, and that's just simply equal to this minimum contrast divided by the minimum contrast plus the semi-saturation constant, and we can solve that for the sigma value and reparameterize this Michaelis-Menten function in terms of that particular parameter. So we have the response gain, and this is the contrast gain G there. These are just the same function reparameterized. Okay, so in our experiment, we tested 27 observers, 9 normal trichromats, 9 protanomalous trichromats, and 9 deuteranomalous trichromats. We tested each one using maximum likelihood difference scaling on 2 axes, one a luminance axis and one the LM axis, and the Arrington-Kraskov many color space. Okay, so this shows a typical trial. The observers were pre-tested with a number of standard tests. They were tested over 4 sessions with about 6 runs per session, alternating between the 2 tasks. We used 9 contrasts, which for a single run gave 84 triads, which they can complete in about 5 minutes. The stimuli were horizontal Gabor patches for plus or minus 2 sigma of the Gaussian envelope, 4-degree diameter. The Gaussian, the sine wave was 1 cycle per degree, presentation 0.5 seconds, and these were fixated there at the 2.8 degrees eccentricity. There was an initial test where we estimated this for everybody, where we estimated this minimum contrast they could detect, and so the minimum contrast used was 1.7 times that. Now, when we fit when we estimate the scale values that best predict the observer's judgments over all of the presentations, we get these different scales. This is the black you're seeing for luminance. These are the 9 normal observers, and the open circles are for the LM contrast. And so you can see the lines are the best fit Michaelis-Menten functions, and you can see that on this nominal contrast scale, the observers require more. This is not cone contrast; they require more contrast for the LM, but they're quite similar. Okay, if we look at the protonomalous observers, we see that on this nominal contrast scale, the functions are shifted over more, they require more contrast, and there's a suggestion that they may rise more steeply, but the unexpected finding was that they also peak at a lower maximum contrast. So they seem to have both a higher contrast gain and a lower response gain. Okay, and we see a similar type of result in looking at the deuteranomalous observers. Now, this is just by appearance. We wanted to quantify this. We fit a model. We fit this model to the data, to the two conditions, and this is showing just the average curves for the luminance. This is on the log contrast axis. This is the average Michaelis-Menten fits for the normal protan and deutan observers for the luminance contrast, and these are the average. This is the fit to an average observer for the L minus M contrast, where you can see very well the steeper gain that these are shifted over, but also the lower response gain. Here are the response gains fit to the luminance axis. You can see there's no significant difference for the three types of observers. And here are the response gains, the maximum value fitted for the L minus M contrast. You can see that they're lower, statistically significantly lower for the protan and deutan observers. And these are the gain, the log of the gain. You can see that there's no significant difference, again, for the luminance on average, but there is a higher gain for the deutan and protan. So this supports the hypothesis that Don McLeod originally proposed in his Reese lecture, that and demonstrated also in the MDS results of Bemidol, that there is this higher contrast gain compensation in the anomalous trichromats. It doesn't explain the lower response gain, and I will have something to say about that at the end of the talk if there's time. But now I want to switch gears a little bit and refer. One of the reasons we did this is we were interested in testing the effects of the enchroma filter on these functions, on these contrast gain functions, these contrast response functions. And so here are, we wonder about the long-term effects of wearing a color notch filter on contrast response. So this shows the optical density spectra of two versions of the enchroma filter. This is an outdoor filter. This is one for indoor. You see the optical density to the left. You see the notch here right around 580. And this is, the red is a neutral density filter that we use as a control in some observers. With the observers, you'll see were asked to wear these on a regular basis, but mostly they wore the indoor filter because this all took place during the campfire in Northern California, where people stayed inside most of the time. So we tested 8 anomalous trichromats and 2 normal trichromats. 7 of the anomalous trichromats were asked to wear the enchroma lens as much as they could for about 12 days. They kept a diary. They wore about 7 hours every day. 2 were protonomalous, 5 of them were deuteranomalous. And one of the protonomalous observers was given the neutral density glasses that I showed you. And of course, the observers were not told what type of glasses they had. But of course, when they wore them, so it was blind, but of course, when they wore them, they could see or not see any effects. 2 normal trichromats also were asked to wear the enchroma glasses as a control. They came back into the lab 4 days, the first day before they wore the glasses, 2, 4, and 11 to 12 days afterwards. There were separate tests on each day for the luminance and LM contrast modulations, and we recorded spontaneous comments. The important point about this is they wore the glasses, but we tested them without the glasses, because what we were interested in is what was the effect of the glasses on their visual system, not what was the effect of the glasses themselves. So this differs a little bit in what Lucy was testing. So these show the results from one deuteranomalous observer for the black in the luminance function, luminance contrast function, red in the LM contrast function, the chromatic function. This is on a linear scale. That's where the curves look differently. These are the tests at day 0, day 2, day 4, and day 11. We found that there's some individual variation in the heights of these curves. So what we did was we took the chromatic response and we divided it by the maximum response on day 0. And we could use that kind of as a change in baseline. So here's the first day and here's the maximum response. And what you see is by the 4th day, their response maximum is increasing. Okay, so, and we found that to be systematically the case in all the anomalous observers who wore the glasses. If you want in the discussion, I can show you all the observers to save time. I won't show all the observers. You can look also in the current biology paper that was published a few months ago. To summarize, okay, this observer, they made comments when he wore the glasses. As I said, the people like to wear the glasses. They make things look more colorful. He said the fall leaves seem super vibrant. I look at them while driving, probably not a good thing. Not sure, but believe, day 11, not sure, but believe I'm seeing clothing colors that I didn't see before. And we got a lot of comments like that we reported in the article. And the average change, the maximum change is 85% change for this observer in the Rmax value. Here are the summary results, the average of the 7 observers. First of all, here's the average change in the Rmax of the 2 color normal who wore the chroma glasses. The green are the average change for the 1 proto-anomalous observer who wore the neutral density glasses. So no change, but the average of the 7 observers, we see this change over days where there's a change progressively in the response gain, but not in the contrast gain. Okay, so that's a different. We saw an increase in contrast gain in the anomalous observers with respect to the normal, but when they wore the glasses and when they took the glasses off, we saw that the effect of wearing the glasses was to increase their response gain. Okay, so just one more thing, if I have time. As you saw, the expected anomalous chromatic response from the spectral shift hypothesis predicts when you just have the spectral shift, there's no prediction of gain. Here's on the log contrast, here's the normal curve. If we just look at, this is for a proto-anomalous, if we just look at the effect of the pigment shift, you get the dash curve. So it just shifts over and stays the same shape. If we introduce the contrast gain multiplication, you see it does increase the gain, but it also it doesn't predict a change in response gain. So, but what we do observe, is shown by the red curve, is that there is this reduction in response gain. The same thing in the deuteranomalous observer. So we wondered about what could be causing that, and one hypothesis had to do with the question that we were often asked, that how come when you're multiplying the contrast by this gain, it's not affecting the noise as well? And so we looked at what would happen if we simulated an observer doing an MLDS task when there was noise introduced to the contrast. Now we could look at additive noise and multiplicative noise. I'm going to show you the results from multiplicative, but we get a similar result with additive noise. So here we used noise that was distributed as a gamma variable with a mean of 1. What we did was we had in the simulation on each trial, we had gamma noise that multiplied the contrast for each of the 3 contrasts before they were combined together in the decision rule to make the decision on each trial. And then we fit the MLDS function. So in these curves you see here, there's the same Rmax, the same mean standard deviation of the noise, and the only thing that differs between these 2 curves is the gain. So the blue show a low gain condition, which is similar to what you see in the normals. And now simply by increasing the gain here by a factor of almost 3, you see that there's increase in the gain, but because of the noise, the curve is tailing off. It's also reducing the Rmax. So it's suggesting that reduction in the response gain could be due to noise in the encoded contrast. This raises an interesting question. When we saw the results from the initially in the article, our speculation was that this increase in the response gain might have to do with some kind of perceptual learning. The anomalous observers have a weak red-green signal. The enhancement of the glasses might have, we hypothesize, might have led them to believe, to be more confident about the weak signals they have, and they'd learn to detect them. But this simulation raises the issue of whether the long-term exposure to glasses somehow influencing the noise in their visual system, so that they're able to increase the response gain. So it affects the response gain in some fashion. So let me summarize here. You can estimate contrast response scales very rapidly with the MLDS technique. What we found was anomalous trichromats showing elevated minimum contrast. Well, I didn't talk about that. That can be, but this can be accounted for by the spectral separation hypothesis. I didn't show you that, but that's in the JOSA A article. The anomalous trichromats show increased contrast gain, but reduced response gain for LM chromatic contrast. The reduced response gain is consistent with the hypothesis that contrast gain increase also amplifies contrast noise. And then finally, the long-term exposure to the notch filter enhances LM contrast, leads to an increased response gain in anomalous trichromats. Let me stop there, except to, again, give a second set of appreciation to my two collaborators, especially Brennan, Marsh Armstrong, who we collected all these data over a period of a year or two. Thank you.